This graph represents a standard precious metals valuation model, but apply it to a modern rare earth project, and the valuation almost certainly shatters. The professional hazard for analysts lies in treating rare earths like legacy commodities. They do not have deep futures markets, and they do not trade on uniform rules. The trap usually begins with a single, highly promoted metric, total rare earth oxide, or TREO. Mining projects are frequently evaluated based on this aggregate tonnage, but having material in the ground does not mean it can be sold. Geological abundance is entirely different from commercial availability. To accurately model rare earth exposure, you must abandon aggregate tonnage. The math only works when you look at element-specific separation. The actual cash flow of a rare earth project does not sit in the extraction phase. It is hidden entirely within the conversion bottleneck. This chart shows the periodic table of the elements, with a focus on rare earths. This is the foundational map required to understand their economics. Specifically, we are looking at this row of 15 lanthanides at the bottom, plus scandium and yttrium up top. The core economic driver for this entire industry comes down to chemistry. These elements share nearly identical atomic properties. Because their atomic structures are so similar, they almost always clump together in natural mineral deposits. You cannot go out and find a pure neodymium mine. It does not exist in nature. Every extraction yields a mixed basket of rare earth oxides in varying proportions. A project's commercial viability depends entirely on the specific ratio of elements inside that mixed basket. Valuing a mine strictly by its raw aggregate tonnage ignores this internal elemental makeup, rendering the financial model useless. This diagram shows how we solve the TREO trap by physically separating the asset class into two distinct economic streams along this line dividing light and heavy elements. The first stream is the volume surplus, dominated by lanthanum and cerium. These two make up the vast majority of the volume in most deposits, but they serve low-margin industrial applications like polishing powders and glass additives. The second stream is the magnet economy, driven by neodymium, praseodymium, dysprosium, and terbium. Neodymium and praseodymium provide the raw magnetic strength required for modern electrification. Dysprosium and terbium act as specialized additives. They ensure the magnets retain their charge when exposed to extreme heat. That heat resistance is required for high-performance electric traction motors. It is necessary for the massive generators inside industrial-scale offshore wind turbines. And it is a strict requirement for advanced aerospace systems and defense equipment, where failure under temperature stress is catastrophic. This exposes the financial trap. A project might boast a massive TREO grade, but if that grade is 90% low-value cerium, the revenue potential is severely constrained. A bankable financial model must strip out the aggregate numbers and assign element-level prices and specific recovery rates to each individual oxide. A mine provides the raw input, but the chemical separation stage dictates the actual financial return. Moving millions of tons of earth is necessary, but it is the least strategic part of the entire value chain. The true barrier to entry is separating the mixed elements. Because their chemical behavior is nearly identical, isolating them is intensely difficult. Achieving commercial purity requires highly complex infrastructure, relying on hundreds of sequential steps in solvent extraction and ion exchange. A nation or a company can hold massive geological reserves, but they have zero actual supply security if they rely on foreign states to refine those materials. These processing facilities carry severe capital and operating expenses, driven largely by massive acid consumption and complex water treatment systems. Many deposits also contain naturally occurring radioactive materials, like thorium, meaning tailings management requires strict regulatory oversight. Maintaining environmental compliance creates a hard infrastructure cost that directly dictates lender appetite and customer qualification. The final flaw in standard financial models comes from misinterpreting price signals in a market that lacks deep futures contracts. Traditional legacy commodities produce standardized, easily priced outputs with high liquidity. In rare earths, a quoted spot price for a pure oxide almost never equals the cash a mining company actually receives. This chart tracks theoretical value against reality. You start with a high quoted spot price, but intermediate concentrate discounts and impurity penalties strip away margin. The realized cash revenue at the bottom is often a fraction of the headline reference price. Furthermore, downstream manufacturers demand stringent product qualification testing, which complicates negotiated contracts and delays payment. Bridging obscure reference prices to actual realized cash is the ultimate stress test of a rare earth financial model. This visualizes rare earth revenue. Demand drives massive value spikes for magnet elements, while volume elements remain flat. Value relies on this specific elemental basket, not raw deposit size. It requires metallurgical viability to separate them and producing qualified products under strict environmental limits. Finance professionals must aggressively interrogate processing routes and product forms rather than relying on broad resource drill results. Only by mastering the conversion bottleneck can analysts secure the true financial value of a rare earth investment.